Weak acids. We already talked about the strong acids. Strong acids completely dissociates in the water into its conjugate base and the hydronium ions. Most of the acids are weak acids which ionize only to a limited content. They are not fully ionized. So the weak acids are always in equilibrium in water. As you see, this weak acid is symbolized by Ha. It is when it is in water, it partially this weak acid is partially dissociates into its uh, hydronium ions and the conjugate base. So we can write an equilibrium constant for this equilibrium of the weak acid in water. So we the water the concentration of water is a constant, so we don't include that. So in the numerator we multiply the concentration of hydronium ions and the concentration of the conjugate base divide by the initial concentration divide by the equilibrium concentration of the weak acid. All these three concentrations are equilibrium concentrations. So this K subscripted A is called as the acid ionization constant. So we have a problem. What will determine or what will decide this the amount of ionization? Always this ionization is less than 100%. So how we can determine which acid will have a higher ionization and which acid is having a weak ionization? It depends on the Ka and the concentration of the acid. If the Ka is a greater value, the ionization will be greater. If the Ka is a smaller value, the ionization would be less. Also, when the concentration is higher, the ionization will be higher. Those are those are the relationships. That's the relationship between the ionization of the weak acid based on the Ka, the equilibrium constant of the or the acid ionization constant, and the concentration of the weak acid. Let's see how we can calculate the pH from the acid ionization constant. When we are given the acid ionization constant of for a weak acid, how do we can calculate the pH? What is pH? Yes, the pH is the negative log the hydronium ion concentration. So in order to calculate the pH, we need the concentration of the hydronium ion. Let's look at the example. We are given the HF, that's a weak acid. The initial concentration of the weak acid is given as zero point 0.5. So we write the equilibrium constant expression for the dissociation of the weak acid HF. We have the products in the numerator, so we multiply the concentration of the hydronium ion by the concentration of the fluoride ions divided by the equilibrium concentration of the HF, the weak acid. Then we set up this ice table. This is the reaction and this is the initial concentration. The initial concentration of the HF is 0.50. It is given. So we don't worry about the concentration of the water. The initial concentrations of the H3O plus is 0, F minus is 0. Then what is the change? We do not know the change. So we assume it is as X. So then the change for the acid would be minus X, and for the hydronium ion it is plus X, and for fluoride ion it is plus X. Next, the equilibrium concentrations. For HF, it will be 0.50 minus X, and this is X and X for the products. So then we plug these values to the equilibrium ion expression, equilibrium constant expression. Ka equals X times X divided by 0.50 minus X. We are also given the Ka value for this acid as 7.1 times 10 to the negative fourth. So we assume this X is a negligible value. So approximately 0.50 minus x equals to 0.50. Here is a typo. This must be 0.50 minus x equals that. Therefore, the equation rearranged to x squared, x times x squared divided by 0.50 equals 7.1 times 10 to the negative fourth. So then we solve for x and we found the 1.9 times 10 to the negative second molar for the x. So what is this x? Yes, these are the values for the x. So HF, we subtract that the value of x from the initial value and we find the equilibrium concentration for HF as 0.48. And this is the x and this is x, so they are directly equals to their value. So how do we calculate the pH? Yes, the pH is the negative log of H3O plus concentration. So we get the value as 1.72. pH equals 1.72 for this solution of HF. And then we calculate the percent ionization. This is the initial concentration and this is the amount of the acid ionized. So multiplied by 100, look, only 3.8% of the acid was ionized to its conjugate base and to hydronium ions. So that ionization is very low. Another practice problem. The Ka of hypochlorous acid, HClO, is 3.5 times 10 to the negative 8. Calculate the pH of a solution at 25 degrees of Celsius, that is 0.0075 molar in HClO. Right, so the first thing, we'll write the equation for the uh, HClO ionization. So it is HClO with water. We'll get the H3O plus hydronium ions plus the ClO minus. So we write the Ka for this as the concentration of H3O plus, equilibrium concentration of H3O plus multiplied by the equilibrium concentration of the ClO minus divided by the equilibrium concentration of the HClO, hypochlorous acid. Right. Next, we construct this ice table. The initial concentration of HClO was given as 0.0075. We don't worry about this. And then the initial concentrations are not given for the H3O plus or ClO minus. So we assume they are 0. The change is negative X, positive X, and positive X for the products. So the equilibrium concentration for the acid is 0.0075 minus X and X for the products. Then we plug those values for the Ka equilibrium expression, which is equal to 3.5 times 10 to the negative 8. And then we assume this 0.0075 minus x is approximately equals to 0.0075. So then we solve for this x and we get the x as 1.62 times 10 to the negative fifth. So when we divide that by the initial concentration, we get the percent of ionization, which is less than 5%. And we calculate the pH. pH is the negative, so this is x, which is equal to the 1.65 times 10 to the negative fifth. So that was plugged here, and the pH of the solution was calculated as 4.79. So here you will see the relationship between the percent ionization of the weak acid and the original concentration. When the ionization, if the percent ionization is 100%, we don't get then there is no, okay, the concentration, right? So when the concentration, like the 100%, look at the ionization is 100%, then the concentration is 0. When the ionization is reducing, means the concentration is also going decrease. Now that the percent ionization and the concentration of the acid is going to be mathematically explained using this question. Determine the pH and percent ionization for acetic acid solutions at 25 degrees of Celsius with concentration of 0.5, 0.0, 0.015 and 0.0015. And we are given the Ka for the acetic acid as 1.8 times 10 to the negative fifth. Right, so we write the equilibrium constant expression for the dissociation or the ionization of the acetic acid. We get the product as hydronium ions and the acetate ions, and we construct the ice table. Okay, so let's solve this, construct the table for the condition A, taking the initial concentration for the acetic acid as 0.15, 0 and 0 for the products, minus x, the change, plus x for the products, and the equilibrium concentration is 0.15 minus x and x for the products. Then we solve wing for the H3O plus. So you can use that the uh, Ka equals x squared minus the 0.15, and then you solve for the x, and it was solved for the x as 0.0016. Then the pH was calculated for that as 2.78, and the percent ionization was determined as 1.1 for the acid of 0.15. When we use the same format to solve for the condition B, when the initial concentration equals to 0.05, look, now the percent ionization was little bit increased. Solving for the again, when the concentration was even lower, you will see the percent ionization was greater. So the concentration of the acid is getting lower, the percent ionization will be bit increased. It is slightly increasing. Now let's see how we can use the pH value of a solution to calculate the Ka, acid constant for a weak acid. Look at this problem. Determine the Ka of a weak acid, that is Ha, that we know the initial concentration of the acid as 0.25 and pH of the solution was given as 3.47. We can't do anything with the pH value. So what should we do? Yes, we need to change the pH to the concentration of the hydronium ions. So we use this formula 10 to the negative pH. pH is 3.47 and we calculate the H3O plus concentration for this solution as 3.39 times 10 to the negative fourth. Okay. Now we again construct this ice table and the initial concentration was given 0.25 and this is the hydronium ion concentration. That's actually the change. So plus x. So this is that the plus x and that's the actually again that value for the A minus because the stoichiometry is 1 to 1 and that would be then minus that change for the acid. So we solve that here and here are the equilibrium concentrations for products. You can either use this value or you can use the initial value too because this value is really small compared to that the initial concentration of the acid. So when you plug these values to the equilibrium constant expression and you can calculate the Ka. Here is your turn. Please, even I explain these problems. When you are preparing for the test, just stop the video and try to get the answer for these questions by yourself. Aspirin, acetyl salicylic acid, is a weak acid. It ionizes in the water according to this equation. So, hydronium ions and the conjugate base. A 0.10 molar aqueous solution of aspirin has a pH of 2.27 at 25 degrees of Celsius. Determine the Ka. Yes, the first thing, change the pH to the hydronium ion concentration. Yes, we got the hydronium ion concentration. That is actually the X, right? So here are the equilibrium concentrations for those two products, right? And then you can again solve subtract that value from the initial concentration and find the exact equilibrium concentration for the acid. Or that's even it's okay if you use just the that value assuming that X is very small because finally we are going to round the answer. If that is really small, you can get that out. Or if it is a mathematically like a reasonable value, then you can subtract it. So then you plug those values to this equation and calculate the Ka.